I think it took 15 minutes more. So I'm going to be, first of all, careful not to go about time, and I might reduce a little bit of time today because last time I heard, I heard that, people are not happy if I go a little extra time. Okay. So, so yesterday I was talking about, so I'm going to just rewrite this. So X, I have a set, I have a distribution, Px. I define my, for delta greater than 0, T delta n Px, Xn, such that n of A given Xn, the number of occurrences of the element A is close to its probability. This is a deterministic set, okay? So there is nothing random about it. It's just that we define this set, and so we observe the following. So one, so Xn belongs to T delta n Px implies, if I look at this, Px of xi, I get exp minus n times, sorry, this is actually, so I will put it this way with a dot at the top. So h of Px plus or minus delta. Okay, so you know what it means. So I will also indicate, I will also state a definition after this. So then I have, I think there was a small error. I will correct it this time. I have not completed the proof actually. So h of Px. So yesterday I wrote minus delta. This is easier to prove with minus 2 delta. Less than equal to T delta n Px less than equal to exp n times h of Px plus delta for sufficiently large n. So I will actually indicate this. There is a few subtle points. 3, for any epsilon greater than 0. So some small error probability, I'll call epsilon error probability. There exists an index. Okay, so there exists a large enough. I should switch on my video. There exists a large enough. There exists a large enough n. I mean, you have to wait long enough. That's what n is telling me. So that for all n greater than equal to n epsilon, probability that, so I should be careful here. So the probability is with respect to the distribution. So Pxn of xn, xn belongs to T delta n Px. So the probability that I land in this set is greater than 1 minus epsilon. Okay. So I'll make a few. So, so I think, so just a few, recap of how we proved. The first one is essentially, proof of, recap proof, just a very small recap proof. So A, you just, write this and then you will get it. I equal to 1 Px of xi. So you just write it as a product on the elements. So Px of A, Na of xn, and you use the bound on Na of xn, given that you're already in T delta n. Okay. So this is that. See this. So I will make a couple of qualifications. This holds for any n. Okay, there is no holds for any n. So you don't need any n greater than something, n smaller than something, nothing. It's just count, literally. Okay. The second statement, so if you look at the second statement, so this was A, sorry. Oh. So if I look at the second statement, so we have the upper bound doesn't require any n again. Okay. So T delta n px is less than equal to exp n times h of px plus delta. This is true for all n, holds for all n. Okay. So the idea is that you know that the probability p with respect to the x of t delta n px, this we know is less than, is at most 1, right? This is at most 1. And each fellow has a weight, right? Each fellow has a weight. That is this weight. So each fellow has this weight. So at least with the plus. Okay. So remember, the plus is the smaller one, the minus is the bigger one here, because there is an exponent e power minus n. Okay. So you know, total weight is at most 1 kg. You know that each fellow is at least 5 grams. So then you cannot have more than 1000 by 5, right?
Hang on, what is the dot equal to sign?
Yeah, dot equal to, I'm kind of trying to say this, write this in gray. So this guy, what I'm really so the exponent is growing that way. That's really what I'm saying. So what I'm trying to say is this 1 by n log px n of xn, this is growing as h of px. Essentially, that's what I'm saying, plus or minus delta. That's what the log means. So the idea is the following, right? If I don't know whether you should be aware of this. So if so if f of x is growing as e power some alpha x, right, then essentially this alpha captures everything, right? So that's kind of what I'm doing.
Yeah.
Okay. So this bound comes from that. This bound comes from the fact that each fellow is at least so much mass, and the total mass can be more than 1. Then if you observe, I did not prove the lower bound. If you observe, I did not prove the lower bound. I went ahead and proved this. So equation 3. So 3. So what did I end up getting with 3? So 3, I essentially used union bound. And I used the Markov inequality. But the variance form of the Markov inequality is called the Chebyshev inequality. So I used the Chebyshev inequality and I did a union bound. So I ended up with something like this. So probability that xn does, okay. So the probability that xn of xn does not belong to the typical set. So that means at least one of them has deviated. So this I say summation over a indicator function. So, something like this. 1 by n summation I equal to 1 through n indicator function xi equal to a. This deviates from px of a by something greater than delta px of a, log cardinality of x. And I used the Chebyshev inequality. And I ended up, so this is not for all a, the a has been put here. So this I ended up getting at most something like cardinality of x. So cardinality of x, px of a, 1 minus px of a, with an n sitting at the bottom. The n is the critical thing. This is really what you're after. Delta squared, something of this sort, with a summation over a, but then the summation is only over those a for which px of a is greater than 0. I think I get 1 minus px of a at the top and px of a at the bottom. And this is all those px of a for which it is not 0. So a belonging to the support of x in some sense. And that's what we got. So this can be this can be upper bounded by epsilon. Is there a question? Okay, so then how do we get the lower bound? So how do we get this bound? And we will use the argument which I think I did not complete last time, which I will complete now. So from 3, for sufficiently large n, we have xn belongs to t delta n px, px of n xn. This is at least 1 minus epsilon, right? So I have something like this. So I'm going to write this because I have to go on the left here now. Sorry, this is less than equal to, I'm just flipping the left hand side and the right hand side because I need to go on the right. Pxn of xn, and I know that each one is at most so much, so I cannot have too few elements. So that's the idea. So xn belongs to t delta n px. This is exp minus n times h of px. So at most, okay, so that's why you get a minus here, because the minus with the minus will get multiplied to have a plus. Okay, so you have this now. The terms inside the summation do not depend on the summation, they're all essentially constants. So I'll end up getting just for copy paste, I'm going to pull this here, and I have 1 here. So that means I have exp minus n times h of px minus delta times t delta n of px, the number of elements. So the number of elements, so t delta n px has to be at least 1 minus epsilon times exp. So now this object goes to the right, goes to the left, whichever way you put it. So you're going to get, so then the minus will become the plus. Okay, so this minus will become a plus. So you have plus n times h of px minus delta. Okay, and the idea is that you can choose your n large enough so that I can say this is e power minus n delta. So you choose your n large enough. So for any delta, you choose your n large enough, it will squeeze down. So you can make it less than 1 minus epsilon. Okay, so that's all is the idea. So n times h of px. So now you see, I need the n being large enough. I mean, just a technical point. Okay, so n of h of px minus 2 delta. So please make that correction. Yesterday I wrote minus delta, but it's actually minus 2 delta. This point. Okay, so that's good. So what is the import? So let me explain what's going on. See, I mean, all this is just math, but let me explain what's going on. See, so let's take that example. Okay, let me take the example and go with it. Screw it up a little bit. X is equal to A, B, C, D. Let's say Px of A is 3 by 4. Px of B is 1 by so 1 by 4 divided by 3, 1 by 12. Px of C is 1 by 12. Px of D is 1 by 12. Okay, so what is happening? You have your memory register. Okay, you have a bunch of registers and you're observing data. Okay, so this could be, data emanating from somebody's cell phone. It could be, sensor reading of some temperature. It could be a stock exchange price, whatever. It has some probabilistic law. It is random, but you have some idea of what that value is. I mean, not perfectly, but some kind of a likelihood, right? So this is characterized via a distribution. And so if I so I want to communicate whatever I observe. So I want whatever I observe, I want to let somebody else reproduce that. I want to be able to communicate it, right? I mean, that's what we are doing with our phones or anything, right? Essentially, something that we observe is getting transmitted the other place. So you want to do that. And so if you look at this distribution, it appears I need 2 bits to index every possibility, right? So if I say, no, I'm not going to use 2 bits, I'm just going to use 1 bit, then I can only represent 2 possibilities, in which means I won't be able to, there is just absolutely no way of ensuring that the other person pretty much sees what I see, right? The probability will be 1/12 of the times, I mean, 1/6 of the times, he's not going to see the symbol that you will see if you use only 1 bit to index and give that bit. So what am I doing? So now I bring in the probabilistic aspect, and I observe that as xn scales, right? As xn scales, so initially the mass distribution was 3/4, 1/12, 1/12, 1/12, right? This was 3/4, 1/12, 1/12, 1/12. Now, when I take xn, n is very large. So how does the probability distribution look? So xn, if you observe, the size of xn is 4 power n, okay? But the size of t delta n, px, is growing at a much slower rate, okay? So this is 2 to the power 2n, so I need 2 bits per symbol, right? This is not so much. This is 2 to the power n times h of px plus delta. And you can calculate this probability. You can calculate this. You're going to get much less than 2. And as I told you, this is an important point to, I mean, you would have observed it, but I don't know how much you dwell on it. So if I look at 2 to the power 2n, I plot 2 to the power 2n, looks like this. In comparison to 2 to the power n h of px plus delta, that will look something like this. I mean, literally like this. So your t delta n px is here, okay, or make it large enough, it's here, right? And what it is saying, this has 1 minus epsilon probability. So you can choose your epsilon as small as you want, 10 power, astronomically large, astronomically small. I mean, atomically small. So 10 power minus, 700 maybe. There is an exponentially large set here, exponentially large set. This is growing at a much larger rate, but there is no mass that is falling there. So it's not going to occur. So there's no point in wasting your indices in all these locations. Don't, that's what you would do if you would use 2 bits, right? So if you use 2 bits, you would be indexing all the guys. You're just wasting your resources because it's not going to occur. Okay. And if it occurs, with probability 1 by, 10 power 700, and you can give up at that time. I mean, you can give up once in 10 power 700 times. You can't give up once in 6 times. But you can give up once in 10 power 700 times. So that's really what's going on. So in order to communicate what I observe with almost certainty, I need only h of px number of bits. So I can distinguish every sequence. Remember here what is happening, if I just index, if I just use one bit to index 4 possibilities, I won't be able to distinguish all sequences. But when I do this concentration, I am able to ensure that I distinguish every sequence that I observe. I am being clever, so I'm not going to waste indices on sequences that don't occur, and there is a careful way of doing it, right? So this tells you that the and observe one more thing. So if I take another distribution with the same h of px, then it has, I can use that same kind of indexing mechanism to encode that. I mean, well, the encoding will be different, but essentially the number of indices I require is only so much. So it's like your truck, right? So you have a container, and they tell you, you can put 1 kg in it. You can put either gold, or you can put silver, or you can put sand, or you can put anything, right? So something is quantifying the uncertainty. So also remember, that guy who doesn't know the realization of the source, so the moment he gets so many bits, you are revealing the outcome to him, right? So his uncertainty about the source is gone. See, one more interesting thing is the following. I mean, if you see this lemma, this lemma is actually very thought-provoking. See, what is the first equation saying? I mean, the first statement saying. The first statement is saying that each sequence in that typical set is almost equally likely. So it's really beautiful, because what it is saying, if you think of it, the size of T delta n px is exp n times h of px. And I mean, with a plus or minus delta, right? I mean, essentially, so this is what I mean. And each sequence in that thing is exactly 1 by T delta n. So it is becoming uniform on that typical set. Okay. So what is happening? So think of the following, right? So suppose, so I will just assume I'm not able to calculate this. So suppose this is just, let's say it's 1.2 or something. Then, so what do? I take, one million, 1 million as my n, right? So I need 1.2 million bits, right? And what is happening is all these 1.2 million indices are uniformly likely. So it's as though you have converted the source to a uniformly likelihood source, right? And you're compressing. So in some sense, there's one unit, right, that you're kind of transforming it to. So these things motivate us to define the entropy. So definition. Suppose X is a finite set and Px is a PMF. So PMF, when I say it's a probability mass function distribution, sums to 1 and they're all non-zero. Probability mass function, that's going, kind of terminology. Is a PMF on X. The entropy of PXC, it's really a functional of the distribution. Okay, people, what they do generally is that, they say X is a random variable with distribution, with probability mass function Px, and they define the entropy of X instead of Px, but I will just, use h of Px. So the entropy of Px is the entropy. So 1 second. There's an important definition. So entropy h of Px is, So h of px, this is a definition, important one. You will see this through and through and through. You will see this become one Newman entropy in the quantum case. Minus summation x belonging to x, px of x log px of x, with the convention that 0 log 0 is 0. This is by continuity. Okay, so that's an important definition. Now there will be more such, there will be one more. I mean, this T delta n px is an important set. So I will now use this to prove something more interesting. Again, that is a quantity that you will see in quantum also come across. It's also there in statistics. I mean, most of you would have seen this. Okay, questions, thoughts, ideas, concerns?
So I just had like one high level question.
Yeah.
So I like understand all of the definitions and stuff and the proofs as well. But what I've not like I haven't still yet understood like when you drew that diagram about uh the typical set is much smaller as compared to the whole set. So like my question is when we are, let's say, sending some kind of information from one source to one destination, what exactly are we sending, and what is the significance of the typical set in that whole process? That's what I'm not getting.
Yeah. See, if you're observing, let's say stock prices, right? And you have some knowledge of the distribution of the stock price. You have some knowledge of the distribution of the stock price. What you do is, so let's say the stock price, for simplicity, let's say the stock price takes values in, 1 to 100, and just discretize it. Okay. And you have some distribution on the stock price. What really I'm saying is that, so go and identify this. This is, hard coded. You can go and identify this guy, right? You choose what probability which you want to give up your hand, and, choose your delta, do whatever, you wish, like, look at these above theorems and do that, and identify T delta and px. And so, this, let's say that the distribution, so, I'll make life simple for myself. I'll just say this is 256. So there are 256 values, which means I need 8 bits to index that. But suppose the entropy of h of px is just say 3 bits, because you have some distribution that gives you this entropy. So you need only you need only 3 bits per observation. So what you do, you wait for your stock price for for a long period of time, right? So you see your stock prices, and that with very high likelihood will fall within this typical set, and you would have indexed each one of them. Okay, so you would have indexed each one of them. This size is only 2 power 3n. Okay, so you would have used 3n bits to index each fellow here. Okay, and so you will observe one of these sequences. So I will enlarge the picture just for so these are all n length sequences. So let's say n is say 1000. So you see 1000 consecutive stock prices, and you would have needed 8000 bits, right? Because each possibility is 8 bits. You'd have needed 8000 bits, but you really only need 3000 bits. So the number of sequences here is only 2 power 3000. Okay, so you would use them with 3000 bits, you index them, and you send those 3000 bits to the other guy. So essentially you have saved on 5000 bits. You understand?
Yeah, that makes sense.
Okay, so that's that. Okay, so now Mhm.
So the point is basically to find a set that occurs with high probability but is small, right?
Yeah,
And
exponentially, not small, exponentially small. That's the
right.
word. Yeah,
Okay. And in none of our proofs or bounds did we actually use delta. I mean, it holds unanimously for all delta.
correct.
So why would you ever why would you ever use delta non-zero? I mean, you might as well take zero It
No,
gives
no,
you the
you
cheapest
can't take
possible.
delta zero. Here you have a problem, right? Remember, the Chebyshev inequality is only, you will never get, it's a good question you're asking. See, I'll tell you the following, it's very interesting. So suppose the probability of head is 0.5 and tail is 0.5, and you toss 1 million times, the probability that you'll get exactly 500,000 heads is zero. Zero. Okay, it is zero. So you have to give that margin. Okay.
Right.
So if you don't choose, what happens if you choose your delta to be very, very small, then your n will blow up. So you have to wait for a very long time. So there is this trade-off between the delta and the epsilon.
Right. Yeah.
That's why you need. So remember one more thing. Every sequence, the probability of every sequence is going down to zero as n goes to infinity. Every sequence. It is
Yeah.
that when you pull things up, you are getting a mass. That's
Yeah.
important. And remember one more thing, okay? You'll be surprised. I mean, it's not surprising. You have to be slightly careful. Okay, so this is a nice example. I'll just tell you a nice example here. I mean, just to give you some intuition. So let's say probability of head is 3/4 and probability of tail is 1/4.
Right.
Okay? And if you look at the typical set, right, what it is doing? It is actually looking at, 3/4 of the occurrences must be head and 1/4 must be tail, right? I mean, with some delta. These are the sequences it is pulling up in that set. But
Yeah.
you'll be surprised that these are not the highest likelihood sequences. The highest likelihood sequences are the sequences where you will have all heads, right? This is the probability of a sequence with all heads. Probability of a sequence with k heads, no, sorry, yeah, L heads and n minus L tails is this, and this is the probability. So this is maximized when L is full n, right?
Yeah.
So you're not taking the highest likelihood sequences. You are taking that because the number of them is very small, so they won't collate. I mean, they won't aggregate. So you're
Yeah.
looking at a very nice set where the probabilities is not too low, but they aggregate so that they give you that. Okay, so you'll have to do a little bit of thinking on this. It's not that straightforward, actually.
Right.
Remember, the count of the most number of sequences is the half-half sequence, because that has the highest exponent, the count.
Yeah.
But the
Yeah.
mass on that is smaller. So you
Yeah.
are typically choosing a combination of mass and count so that you are aggregating your mass. So
So is it possible to prove that this is like the best
yes,
ratio?
yes, you can show that if you go for any exponentially smaller set, you have to be
Yeah.
careful. Exponentially smaller set, then that set will not have that set will strictly leave out some mass. You can't tend that to epsilon to zero. So here, if you observe, as n goes to infinity, that t delta n concentrates to that exponent. The rest of the thing will, so the probability of the rest of the thing will go down to zero.
Yeah.
You can show that any other sequence of sets. So let me put it this way. I'll be careful here. So I'll make the statement. I mean, slightly heuristic, but I'll make the statement. Suppose an is a sequence of sets, okay, such that, I'll be very careful here. So limit as n tends to infinity 1 by n log an, size an. Okay, so an is a sequence of sets, they're blowing
Yeah.
up. But if I look at the exponent, how it grows, if this is strictly lesser than h of x,
Yeah.
then you can show that limit n tends to infinity, probability of an goes to zero. Zero.
Okay. Oh, wow.
I mean, well, you need maybe some delta here. I'm being slightly, I think you'll have to show some lim in for something of that sort. I think
Okay.
you need some lim in for something of that sort. So, what have you done? What have you done? You have left out something here. You have left out something here, right? You have, so when when it is less than h of x, right? You cannot take everything here. You cannot.
Yeah.
That means you have taken something, you have left out some exponentially many.
Yeah.
And so that fellow will contribute and ensure that there's some problem. Well, I have to be slightly careful here. Maybe it is not. Let us be slightly careful here. Maybe it will not go to 0. I think it will strictly be less than 1 or something. I have to be slightly careful here.
Okay.
But I can make that statement. But good question, very good question. Yes, this
Yeah.
is exponentially the best sequence you can get.
Okay.
Okay, great. Thank you. That's a good question. I will try to make that slightly more. I'll give myself a little space. Yeah. Okay. So now I'll come to another important lemma, an extremely important lemma. I will also use that to define something. So let me first define, because I think I will. Yeah, let me just define. Suppose Px and Qx. Just one more point, just for those of you who were there in the organizational meeting. So this is also the Gibbs entropy. Turns out, okay, this was done in statistical physics. So this whatever I am stating is coming from Shannon's work in 1948. So this is a completely, as I told you, it's an engineer and a mathematician trying to do something for data compression. But this turns out it has exactly the same definition as in statistical physics. So you can see the connections come through. Okay, so so suppose Px and Qx are probability mass functions on X, then so there are multiple definitions here depending on which area you see this definition in. Kullback-Leibler divergence, d of Px Qx, or the relative entropy. This is more in I think I don't know what is the term used in statistics actually. This is used in quantum, so I will just put that also later. Is defined as d of Px Qx is summation x belonging to x Px log Px of x by Qx of x. You can see why it is relative entropy, because the entropy terms are appearing, or plus infinity if whenever Qx of x equal to 0 implies Px of x equal to 0. So in other words, I'll if for some a belonging to x, Qx of a equal to 0 and strictly Px of a is not equal to 0. Okay, so what is happening? So maybe I'll just write a small picture. So essentially, so support of Q and support of P. Okay, let me just leave it like this, and then we'll make this more clear. So what am I doing? I have two distributions now. So I'm kind of, this is a this object is kind of a the divergence or the distance between two distributions. So what am I doing? I'm looking at the set X, and I'm looking at the space of all distributions on X, space of all distributions on X. And I want to kind of give you a feel of how far two distributions are, how close two distributions are, and things like that. That's what I want to do. So this is a notion for that. This is not a metric. It is not symmetric. It's not a metric, but it satisfies the Pythagoras theorem. The parallelogram, sorry, law. It satisfies the parallelogram law. And we will see its application in a couple of lemmas. Okay. So so I'll just leave this here. Okay, so what do I want to do? So I give you some motivation for one hypothesis detection problem. How many of you have seen Stein's lemma? How many of you have seen let's say how many of you have seen what's that called? I mean, false alarm, misdetection, statistics. How many of you? I mean, I know some of you have a background in statistics, so I'm just asking. Because I won't. Okay, anyway, it doesn't appear that not. I mean, at least I'm not seeing too many raised hands right away. Okay, so consider the following scenario. You're trying to. You have a sensor. Okay, so I will physically motivate this, and then I will explain what's going on, and then I will state the lemma, and then prove it. So think of yourself having a sensor. Okay, it's a temperature sensor. Okay, and so you are installing it in your classroom, and you want to ensure, and it's just reading the temperature, and you want to link it up to an alarm so that if there is a fire, the alarm starts ringing and people get out. And the key point here is that at what threshold will you let the alarm fire, right? So you have this temperature scale, and you want to decide where you want to put your threshold so that there is fire above that and there is no fire below that, right? So observe the following. If you set your temperature very high, I mean, sorry, this threshold, so let's call it T. If you set this T very high, then you will miss a fire, right? If there is a fire, the temperature has not gone that much, your alarm is never alerted, and there is a problem. If you set it too low, then it keeps it's a false alarm, right? Every time it says there's a fire, but there's really no fire. And there is no way to make it perfect, right? Because at any temperature, it could be that the fire is too localized and you don't see the fire. So or you have for some other reason it's got too hot, and the temperature, the alarm has sounded. So there's no perfection, right? So there's always that trade-off. So what do you want to do? I mean, think of really doing this. You don't, I mean, lives are important, so you don't want to miss a fire. Whenever a fire happens, you definitely want to say there is a fire. But it is okay at certain times that you give a false alarm, people get out, but then they realize there's nothing and they come back. This happens actually all the time outside. So you want to ensure. So what do you do? So your misdetection. So MD is your misdetection. So that is, there is a fire, but you don't call it. So this I call the misdetection. And this is critical. You don't want to miss detection, right? So you put a constraint on your misdetection. So the goal, identify T. So identify T. I'll come to the statistic problem very quickly. Identify T, the temperature, the threshold, so that the probability of misdetection is extremely small. Okay, you choose epsilon to be extremely small, 10 power minus 700 or something like that. So only 1 out of 700 times there is a fire. 1 or 10 of 1 to the power 10 to the power 700 times there is a fire. You don't, and people die. Okay, but and then given this, you want to minimize your probability of false alarm. Minimize probability of false alarm. So constraint is, so you understand the difference between constraint and objective, right? Constraint is something that you're not going to budge on. Objective is something that fine, I mean, I'll do my best. Okay, because this asymmetry is important in the problem statement, so I'm just trying to motivate it with an example. Okay, so now, so Px is the distribution of the temperature. Suppose there is a fire. Okay, when there is a fire, obviously the distribution changes. If there is no change in the distribution, you cannot tell, right? Only when there is a change in the distribution, you can tell something is happening, right? So Px is the distribution of temperature when there is a fire. And Qx is the distribution of temperature when no fire. Okay. So what do you want to do? You want to come up with, so you have set of all observations. Xn is the set of all observations. You're observing your temperature, sequence of temperatures. There'll be a time when something happens and then you want to tell, right? So, so I have my Xn, right? I want to partition it into two sets. So that T, right? Really, a T, I'm just partitioning it, a threshold. T, I'm partitioning it. So, so I'll say this is the set of all those sequences for which I will say fire. Okay, and anything outside, I will say it's no fire. Okay, so that means if my observations fall within this set, I will say there is a fire, and I'll ask people to get out. If the observation falls in this set, I'll say there's no fire. Okay, so what do you want to ensure? So this is your so dp xn belonging to xn such that you call p. Okay, and dq is your decision region, xn belonging to xn, you call q, and this is essentially xn minus the set dp. Okay, what is my constraint? So let me write down my constraint and false alarm. I want to fix the threshold. So what is really the threshold? I really want to fix what is dp and what is dq, because as I move this as I move this lever, I mean this kind of a set, the probabilities will change, right? So really I want to check where to put my dp, where to put my this separator. That's really what I want.
Exactly, Xn is the set of temperatures.
Yeah, xn is a set of all your observations.
Okay.
I mean, this is I'm giving a physical motivation, but there is a general problem out there which I can state.
Okay.
Okay, so so what is the probability of false alarm? The probability of false what is the probability of misdetection? The probability of misdetection is that your observations fall in dq. So in which case you don't say it's a fire, right? dq is the set of all those sequences where you call q. Call q means no fire, let people live. This is when you call p. So what is the probability of misdetection? The probability of misdetection is under the law p, you fall in dq, right? So this is actually there is fire. So the data that you're getting is according to the distribution p, the temperature, but you end up falling in q. That's your misdetection. What is the probability of false alarm? Probability of false alarm is that it's generated according to q, but you ended up in the set p, right? Q, x, n of this is important to understand this, otherwise you will not get it. So dp, okay, this is important. Okay, so what do you want to do? You want to so the goal is design dp so that I want to minimize. So I want to, so I have this. So xn belongs to dq pxn of xn. So I will say this is xn minus dq dp. Okay, because dq, remember dq is xn minus dp. So that this is greater than equal to 1 minus epsilon. This is a constraint. So the probability that under a fire, I fall in a set which I don't call fire. And then subject to, so that subject to, and you want to minimize this guy, right? xn belongs to dp of qxn of xn. You want to minimize this. So you want to minimize this. Okay, is the objective and the constraint clear? The constraint is coming from nature. You don't want to, when there is fire, you don't, it's okay to sometimes say, there is a fire when there's no fire, but you don't want to do the other way around. That's important to understand this asymmetry. Okay, So I want to, so now I have to identify DP. Observe the problem. Identify
Just
DP.
just
Yeah.
one question. So
Yeah.
the constraint should be an upper bound, right? Like we want the probability to be.
Yeah, you're right. Thank you. I think so let me do this. So maybe let me do this. Thank you for that. I'll put this 1 minus epsilon. Is that okay?
Yeah.
So I want the probability that I fall in that set to be greater than 1 minus epsilon. So whenever there is a fire, I better fall in that set. That's really what I'm saying. And when there is no fire, the probability that I fall in that set should be small. So you see, there are two constraints here. Not only I have, see, I can make the entire set dp. So every time I can say fire, but then I will be meeting the constraint because it's one every time I say fire. But the problem is the false alarm is too high, right? So that's what I want to minimize the false alarm. Okay, good. See, the point you have to keep in mind here is that the set xn, this is growing exponentially. Okay, and you are trying to so this is a very highly very extremely hard. So you are searching among an exponentially many sets. So how do you search this set? It's not easy, right? Because your choices is too high. It's just growing exponentially. 4 power n, you have to find a subset in that set of size 4 power n. The number of subsets that are growing also. That's also growing exponentially. It's actually growing doubly exponentially. And there's no constraint on the size or anything of that sort. This is a impossible problem to solve. So what we will, we'll essentially solve the problem, but that's where your ingenuity comes. So what I will do, see, n is going large, so I don't want just this to be minimized. I want this to fall exponentially. So I'm very ambitious, and I will say not just this. I want to minimize the rate at which it falls. So this thing is going to, you will see that this thing is going to fall like e power minus n times some quantity, let's say beta. I want that beta to be very large. Okay, so I want it to fall exponentially. I want to find the best beta. Okay, so not just minimize, but it should just like completely get squeezed out. So I will state the problem. So maximize minus 1 by n log. So when I do the minus 1 by n, I will extract out this beta at which it is falling. Okay, minus 1 by n log xn belonging to dp qxn of xn subject to xn belongs to dp pxn of xn. So observe the difference in the two distributions is greater than or equal to 1 minus epsilon. Okay, that is the goal. Find dp.
Wait, sorry, I forgot which is P and which is Q. P is the fire.
P is fire. Okay, P is problematic. Think of P as problematic. P
Okay,
is
cool.
okay, so I want to do this. What I'll do, I will give you the set and we will go and do something. Okay, so what do you want? What will you guess now that you've done a lot of preliminaries? So I will go and do what I did previously. Now you see why that typical set is important. So I will define. So we'll just go define dp, and we will characterize we'll characterize what is the rate at which it falls, and we will show that it is the best you can get. So that's what I do, and kind of answers the question previously. One of you asked. So dp is the set of all those xn such that n of a given xn divided by n minus px of a is less than or equal to delta px of a by log cardinality of x for all a belonging to x. So this is my set. Okay. I will now let's go study. So clearly, are you convinced that? So I will say clearly, and I will request you to put up your hands up if you get this px. I mean, if you don't get this, put up your hand. This is greater than equal to 1 minus epsilon for n sufficiently large. We have done this, this thing we have done.
Yeah.
So if you don't get it, put up your hand. I will just pour for a minute. I'll just look at the participants, and if you don't get it, put up your hand. If you get it, it's fine. I don't want everybody to have to put up your hands. I mean, through Zoom. Okay. Okay, so you get that. Great. So that means constraint is met. So I'm in good territory, but I'll see how good it is. So let's study this, right? So minus 1 by n log. So minus 1 by n log. Sorry. I'll do a xn belongs to t delta np x q x n of xn. This is what I'm looking at. So far is okay? Anybody not okay, raise your hand. I'll just indicate what's going on. Okay, I think now you know what we should do, right? Kind of know what we should do. We know what T delta NPX is, right? So what is QX? Now you see all the tools that we kind of developed before come into place. So we know this. This is I equal to 1 through n qx of xi. We will use the same trick we used in the beginning, right? So this is, I can say a belonging to x, qx of a, number of times a occurs, but now now I have q here, not p. I have q here, not p. Remember we had p last time. So this is, I want upper bound on this because I want a lower bound on this. I want to maximize this. I want to minimize this because there's a 1 minus 1. I want to minimize this means I want to get a lower bound on. There's at least so much. I want to get a upper bound. So, so this is the following: a belonging to x, qx of a, this is at most, n of a given xn, I know is at least n px of a minus n delta, right? So this is n px of a minus n delta. So
How did we get that step?
so n of a given xn, right? This is maybe I should, yeah, this is at least npx of a minus n delta, right? By log cardinality of x. So thank you. Maybe is that your doubt? So see here, this is my set, right? This is my dp. So I am looking at t delta n is essentially px. So I didn't maybe state that. So let dp equal to t delta n px. Is that okay? One of you who asked the question?
Yeah.
Okay. So that's that. So
There should be another px multiplied to delta.
yeah, thank you. Yeah, you're right. So okay. So this is again a belonging to x, exp n times px of a, uh, 1 minus delta by log cardinality of x log qx of a. Yeah. So this is exp minus n times summation. So I do a couple of algebraic steps. Px of a, you know what? Px of a log 1 by qx of a. So that's why I have got a negative sign outside. Okay. And I have a 1 minus delta by log cardinality of x outside because that doesn't depend on a. And I have pulled the product into a summation in the exponent. That's all I've done. Okay. This is an upper bound on qx of n. So what do I have? So for xn belonging to dp, which is also t delta n px, qxn of xn is at most exp minus n times summation. So I will, 1 minus delta by log cardinality of x. A qx of a, sorry, maybe it's px of a. Px of a log 1 by qx of a. Okay. Now, what do I want? I want this, right? Probability that I'll end up in some sequence in which I design I say fire, right? So this is less than equal to t delta npx, this object. Each fellow is at most so much, and there are so many guys, so I can't have too many. And this I know because this guy I know. This guy is at most exp n times, sorry, exp n times h of px plus delta. So all the plus deltas and all those guys, you can, yeah. So you'll have something like this. So this is at most exp. Let's see. Yeah, so you will get something like minus n times 1 minus delta by log cardinality of x, a belonging to x. Remember, h of px is minus px of a log px of a. Okay, so you will get something like this: px of a log px of a divided by qx of a. Okay, h of px, remember h of px is minus minus px of a log px of a. And when I put it with the minus here, I have to put it in the numerator. Okay, with the minus here. Okay, so that's it. So what have I got? I have got xn belongs to dp, qxn of xn is at most exp minus n times 1 minus delta by log cardinality of x. You can choose your delta to be, arbitrarily small. You can choose your delta to be arbitrarily small, n to be arbitrarily large, so that this epsilon is still satisfied. There is no problem with that. You can always do that. So this is what you get: a belonging to x, px of a log px of a divided by qx of a. Okay, so that is, so minus 1 by n log xn belongs to dp. The probability, the exponent at which this false alarm probability is falling down. The exponent at which the probability of a false alarm is falling down, that happens to be the relative entropy, d of px qx. Okay. So look back here. So we wanted to find a set whose probability, where the fire probability, the probability under fire is very high, but you want to maximize the fall at which you will call false alarm. And so we have found a candidate, we have chosen, we were, somehow we were like, ingenious. We went and identified one such set, and we went ahead and characterized its exponent at which it falls, and we ended up having its relative entropy. But that's okay. I mean, who says this is the best, right? I mean, there's no need to believe that this is the best. But at least I know that the exponent is at least as big as, because if somebody is more ingenious and they find a better set, they will get a better exponent. They can't get a worse exponent because I've already given you a candidate. So that's that. Now we will show that no matter what set you take, you will not be able to fall greater than this. So that means that this quantity has some significance, right?
It's in the fire and no fire analogy. It's like P and Q are complements, but that's not used in the proof, right?
No, P and Q are not complements. That's a good point you're raising. No, see, P and Q are not complements. P and Q are not complements. This is a good question that you raise. P and Q are two distributions. So when there is fire, the distribution will be centered like this. When there is no fire, the distribution will be centered like this. There are temperatures where you can neither say whether it was the blue guy which generated it or the red guy which generated it.
Right.
They don't have disjoint support. No. Complement, I think that's what in your mind. They have disjoint supports. No, they don't have disjoint supports. See, if they have disjoint supports, it's very easy, right? I mean,
Yeah.
it's very easy. That's exactly, you see what this thing relative entropy is telling you. If for some qx you have 0, and for that you have a px probability, positive probability, the moment you see that, you call it as p. You will never make a mistake. So that's why this is infinity. That means the probability of false alarm falls infinite. I mean, it's 0. So if they're complement, the exponent at which it falls, see, if I have 0, the exponent at which it falls is infinity. Any positive exponent means that it is never going to go to 0. Okay, good question. I have 7 minutes, right?
Yeah.
Yeah. Okay. Good. So we will show this. Proof is simple. I mean, it's not simple, but again, you use the ideas of typicality. So suppose somebody is more ingenious and they come up with a set Bn. Suppose Bn is a set Xn such that is a sequence of sets such that n greater than or equal to 1, such that eventually the probability under Xn belongs to Bn of, sorry, there's another candidate set somebody comes up with, Pxn of Xn. So the probability under fire, so they have chosen Bn is when they will say, they'll say it's fire. And this is greater than 1 minus epsilon. Suppose, then really I want to look at this. I want to look at this. So the idea is the following. So let B tilde n. So Bn is some sequence of sets. I don't care what it is. But the idea is that it can't exclude too many of my typical sequences. If it excludes too many of my typical sequences, there is some problem. So it has to have the entire guy. Otherwise, it's not even going to meet the constraint. That's the idea. So let B tilde n be defined as T delta n Px intersected with my the Bn that he comes up with intersected with my set. I know something about B tilde n. That's the whole idea. And now so I know the following. So it's a smaller set, right? So so we know that this is true. Xn belongs to B tilde n. Qxn of xn is going to be greater than equal to, less than this. So maybe I should tell you the intuition before I prove it because I don't have too much time. Oh, I told you that I'll finish early. I didn't.
Same thing twice.
Sorry?
You wrote the same thing twice.
Yeah. 1 second. I thought I wanted to tell you the intuition before I tell you the proof. So what is the intuition? The intuition is that you cannot be excluding too many sets from the typical set. If you are, then you won't hit this constraint. Actually, you know what? You won't be hitting this constraint. And if you take number of them, then they will contribute to your mass. So let's see. So what do we know? We know this, right? This is true. What do I want? I want to find an okay, yeah. I want to find, so what I will show is the following. I want to now show a lower bound on Bn. Okay, I want to show a lower bound on this. So if I get a lower bound on this, then I am in good shape, right? That's the idea. Xn belongs to Bn, Qxn of Xn. This I know greater than Xn belongs to B n tilde Qxn of Xn, right? And I know this. Qxn of, so this. So I'm just using the fact that I have intersected with the typical set. So this is going to be npx of A into 1 plus delta by log cardinality of x. This I know. So then I know this. I'm going to go a little fast here. So I have something like minus n times A belonging to x, px of A log 1 by qx of A, all this that we did, 1 plus delta by log cardinality of x. So far you observe I have not used the fact that I have 1 minus epsilon, right? So I also know this. Yeah, so I know this. Now what I do, I use the fact that I have this Pxn of xn. Xn belongs to B tilde. And what can you say about this? So, okay, I'll tell you. So we have this. We know this. So what do we know here? I mean, now that you've seen everything, I mean, you should be able to answer. So the idea is simple. Idea is very simple. Each fellow has a probability at most so much, right? So your B tilde n cannot be too small. So that you use to, so it's as follows. So this can be written as B tilde n exp minus n times A belonging to x, px of A log 1 by qx of a. So I have to only get a lower bound on, sorry, 1 plus delta by log cardinality of x. I have to only get a lower bound on b and tilde, right? That is, the cardinality of b and tilde should be large. And the idea is that if b and tilde is small, then that means that the probability is small, because each fellow here has at least so much, as at most so much probability. So you cannot have, you should have taken quite a few of them. So you will just show, I leave this here because it's sort of time. You just show that this thing is at least exp.
Wait, don't we need something in between 1 minus epsilon and p and xn? I mean, we need something in separating the first and the second, not behind the second term, right?
Sorry?
We need something separating the first and second terms in
I
that
think,
chain, not behind the
yeah,
second
I
term.
think we need this. So we have, so observe this. Yeah, got it. N times h of p minus n times h of px plus delta. Right?
Okay.
So
Yeah.
so this is b tilde n. No, this is a minus here, because it can be plus. I mean, you're taking the largest guy. So this guy is at least so much. Okay, so this implies that, so this implies this. And so you have, I will complete this in the next class, but essentially you get the exponent. Okay. So this is the Stein's lemma. So you see this Kullback-Leibler divergence. Okay, I will not go over time. I wish to have a class tomorrow to make up for all the all 4 classes that I missed. How many of you? It also helps you because you have to take a decision on the course. I mean, whether to register it or not. And so having more classes will help you before you take a call. So that's the reason I want to take a class tomorrow. Same time, 6:45 to 8. Those of you who want to come but cannot, raise your hand. I'll give 10 seconds, and then I will. I have created a Moodle page. I don't know how it works like this. So I'm wondering if I will not be able to communicate with any of you. That's why I'm thinking the best way possibly is to announce right now. I don't see anybody raising their hand. So I will have a class tomorrow. The reason is twofold. One is I have missed classes. Second is it will help you decide before you.
I don't see the Moodle.
Huh? Yeah, I have not. Yeah, I have just created the page. I have not. I think. I think I have not. Some word for it. I forget. You must somehow share it or advertise it or export it. Something of that sort. I need to do. I see. I know why you don't see it.
Okay.
I'll work on it.
Yeah.
Okay, so I'll have a class tomorrow at 6:45.
Will it be the same meeting ID or a different?
Yeah, tomorrow I will use the same meeting ID. But from next class I will change for sure.
Okay.
Okay.
And also, can you tell us, so is this in like scissor and corner?
Yeah, this is in Cesar and corner, but yeah, this actually is in Cesar. I mean, the Stein's lemma is in Cesar and corner. So what have I done? So I have done a little bit differently from the order they do, and I've also done it slightly differently from what they do. They use some continuity. So the Stein's lemma proof, again, I think his set is different. His Stein's lemma proof, his set is different. So Stein's lemma is actually theorem 1.2. Yeah, theorem 1.2 is the Stein's lemma proof, but I've given a different proof, slightly different proof. Not really. I mean, well, I've used typicality because I wanted to give some intuition for that set.
Right.
And in the chapter 2, he first does types and then he does typical sequences.
Sorry, who?
Cesar and Corner first do types and then do typical sequences. I will first do typical sequences and then do types.
Okay, so that's from chapter 2.
Yeah, and yeah, but if you observe, I have actually proved, I mean proved or proven, I don't know. I have actually proven I have actually given definition 2.8 with a different normalization. If you observe definition 2.8 in Cesar and Corner, I have proven well, for him, everything comes out of type and it's slightly. I have proven lemma 2.12. Only one part, I think. You will actually do the rest. So I will actually give a homework. I have also proven lemma 2.13. And I have proven, well, I have not really proven 2.14, but I've proven 2.13 and I've proven 2.12, one part of 2.12. But I have notes for this which I will circulate, which follows the notation that I have. So I will circulate notes for that, for this part. Pretty much teched up. I should do a little bit of searching to get it out. I will also post a homework, right? Maybe today or tomorrow. Homework extending what I've done to the next. And I want you to do that homework soon because that homework, everything builds on that homework at some point. I mean, very soon.
Okay.
Okay, I will end.
Yeah.
Thank you. Thank you.